Thank you, John. Thank you all for coming. So today we'll discuss black holes in Einstein's gravity and beyond. The outline of the talk is the following. First, I will remind you the relationship between gravity and the geometry of space-time, in particular gravity and the metric. We'll talk about how to quantify this relationship, and that brings us to Einstein's equations. Then we'll discuss the most fundamental solutions of general relativity, such as Schwarzschild, Reissner-Nordstrom, Kerr, and Newman metrics. And then we'll come to discussion of black hole horizons, discuss a little bit coordinate versus true singularities, before coming to a more advanced topic, which involves laws of black hole mechanics, whether or not these laws reflect the dynamics of the real system, Hawking radiation, and black hole entropy. Then we'll come to more speculative topics such as holographic principle and gauge gravity duality. So first of all, we all know to some extent, some people from high school, some people from popular movies or books, we all know the contents of general relativity. Matter and energy curve space-time. They distort the fabric of space-time, and because of this distortion, motion of other objects, for example planets or light rays, around the big object that curves space-time, change. They differ, right? So if you have a light ray coming from infinity and there is some large body which curves space-time, then the light ray will not propagate along a straight line anymore. It will be deflected by simply the fact that it propagates along this trampoline, and the trampoline is curved. So this is a qualitative picture, but of course the question is how to quantify this. And to quantify this, we need to write down equations of motion. The equations of motion of general relativity were written about 100 years ago, and they are Einstein's equations written here, and we'll discuss them in some detail in a moment. So basically, the contents of general relativity is that geometry, which means metric, will be affected by energy or mass, and vice versa. So what are the ingredients of Einstein's equations of motion? The main hero of this discussion today will be the metric. So let me remind you the simplest facts, such as Pythagoras theorem. So if we have a two-dimensional flat space, and we would like to measure distance between points B and C, for example, the distance delta S, then this distance is given by Pythagoras theorem. The distance delta S squared is simply equal to delta x squared plus delta y squared. Then we can take these distances to be infinitesimally small, and then the same line, but now with infinitesimally small elements, applies. We have ds squared, this is called the line element, is equal to dx squared plus dy squared. This is the metric of two-dimensional flat space-time. We can generalize this to 3 dimensions. Now ds squared is equal to dx squared plus dy squared plus another coordinate dz squared. And in fact, why stop at 3 dimensions? We can happily generalize this to 4, 5, 6, and d dimensions if necessary. And so in d-dimensional flat Euclidean space-time, the line element squared is equal to the sum of squares of its infinitesimal displacement. We can put this in a more elegant form, the matrix form, by writing the following expression. ds squared is equal to gij dxy dxj, where summation over I and j is assumed. So this example is given in 2 dimensions. So I and j go from 1 and 2, each index goes 1 and 2, and in the end we should get what we had in the previous slide, namely dx squared plus dy squared. So explicitly, this relationship is written here in this line. We have 4 elements, right? We sum over I and j. There are 4 elements, g11, g12, g21, and g22, and these 4 elements can be elegantly put into 2 by 2 metrics, such as given here, and we can compare this line to this line, and we see that these 2 off-diagonal elements are equal to 0, and g11 is equal to 1, and g22 is equal to 1 as well. So this is a metric tensor in flat 2-dimensional space. Suppose now we generalize this. So in the previous example, gij was independent of x. It was just a metric constant matrix with 1 and 1 and 0 and 0. But in principle, it may depend on point in space or space-time. So for example, we can have, again, the 3-dimensional Euclidean space with dx squared, dy squared, and dz squared. But remember one important thing, that we can use different coordinates. We can use, for the same 3-dimensional flat space, we can use either Cartesian coordinates or spherical coordinates as shown in this picture. and then the line element will change visibly from this to this, right? It's not surprising, because if we change coordinates in this expression, the distance squared will not change. But of course, these coordinates change, and therefore the metric itself, the metric tensor, must change. So in matrix form, it means that in the first case we have this trivial 3 by 3 matrix with 1, 1, 1 on diagonal. In the second case, we see that the metric tensor now depends on the point in space. It acquires the explicit dependence on space. It will be important, then we'll discuss black holes. So some examples of flat metrics are given here. So this is a metric in three flat dimensions. Now we can generalize this more, and this is essentially the contents of the special relativity. The discovery, again made by Einstein and others, that we actually live, at least locally, in 4-dimensional space-time, where this is the spatial part, dx squared, dy squared, and dz squared, but the time is not an independent spectator. We need to put also the time elements into the metric, and essentially the contents of special relativity is that our space-time is locally Minkowski space-time with metric given here. Again, you can write this metric in different coordinates. For example, in spherical coordinates, and again, there is this time element minus c squared, dt squared, but this part is written in spherical coordinates. How do we know that our space-time, is actually curved? What kind of local experiments or non-local experiments can we do to determine the curvature of space-time around us? Now, some people thought about this for a long time, in particular Gauss in the 19th century, and one non-local experiment that you can do is the following. You can draw a triangle and try to measure the sum of the angles in the triangle. If your space-time is flat, you discover that the sum of the angles is equal to 180 degrees. If it is not, for example, if you draw a triangle in a sphere, you can measure these angles and discover that the sum exceeds 180 degrees. If your space happens to be the saddle point, like this one in Lobachevsky geometry, then the triangle, the sum of the angles of the triangle is less than 180 degrees. So this is a test, one of them. You can do more tests, for example, with the same saddle point field, which is known as hyperbolic space or Lobachevsky space. You can do the following. You can draw a circle and measure the circumference, and you discover that on the hyperbolic space, the circumference is greater than 2 pi r, as it were in a flat space, for example. Which is not surprising. Look at the metric. The line element in hyperbolic space is given by this expression with y squared downstairs. So definitely, this is not a Euclidean metric, it seems to be. But then you may ask, all right, so how do I know? Do I know for sure if somebody gives me this metric? Is it surely the fact that the space is curved? Or I can do some coordinate transformation, like on the previous slide, from spherical coordinates to Cartesian coordinates, and actually bring this metric with some complicated transformation back to the flat space. Is it possible or not? So we need to have some local test of whether or not the space is curved. And such a local test is provided by the Riemann tensor. So I will not go in detail to explain what this object is. It is written down, the definition is written down. You can only notice the following fact, that the Riemann tensor contains a derivative of some object which is known as the Christoffel connection, or Christoffel symbol gamma. And the Christoffel symbol gamma itself depends on the metric. So ultimately, Riemann tensor is expressible in terms of derivatives, actually a second derivative, because there is one first derivative here, and then on top of that there is another derivative of gamma. So it is the second derivative of the metric to which Riemann tensor is proportional. Out of Riemann tensor, you can build other important ingredients, such as Ricci tensor and the Ricci scalar. And the important local statement is that a space is flat if and only if its Riemann tensor is identical to zero. So if somebody comes to you and tries to sell a very complicated metric, saying that I found a wonderful solution of Einstein's equation, the space is curved, and this is solution that should be named after me. So you should not believe this person at once. First of all, you should check whether or not the Riemann tensor of this metric is zero by following these formulas. And if you discover that the Riemann tensor is zero, then there exists a transformation which brings this complicated metric back into a flat Euclidean space, and therefore the claim is invalid. So the Riemann tensor and its derivatives will play a very important role in general relativity. Of course, as we saw already in Einstein's equations, so that these ingredients, you now have all ingredients to write down Einstein's equations, Einstein's field equations. Here they are. So what is happening on the left-hand side is basically the second-order partial differential equations with respect to the metric. On the right-hand side, there is an object which is known as the stress energy tensor. This encodes energy and matter contained in space. Okay? So, important statement is the following. Despite the fact that we don't see any derivatives explicitly entering here the equations, they are, as we saw in the previous slide, they are second order, nonlinear, coupled partial differential equations for the components of G mu nu, or Gij, the metric tensor. Okay? So you can, I tried to write schematically, here is the expression of Einstein's equation to the left-hand side, so you could see that indeed we are dealing with the second order partial differential equations. And there is a source for these equations on the right-hand side. You can compare this with Maxwell's equations, where we have the following. So suppose we have a distribution of charges and currents in space, and we would like to find electric and magnetic field generated by those currents. Then we write down Maxwell's equations, and these are also partial differential equations with respect to the four potential A mu. From A mu you can calculate E and B, electric and magnetic field, in all space. So the philosophy is the same. The electric and magnetic field here are sourced by distribution of charges and currents. Here, the metric G mu nu is sourced by the distribution of matter and energy in space. There is, however, a fundamental difference in these two equations. Maxwell's equations are linear. This means that we can find a generic solution, if not explicitly then in the form of some integrals, immediately. And people in the 19th century did exactly that. However, here, Einstein's equations are partial nonlinear differential equations. Generic solution is not known, and it's not unique. It is a very, very complicated set of differential equations. So even in a simpler case, with zero cosmological constant and zero matter source, so suppose we have a vacuum, we don't have any source on the right-hand side, generic solution remains unknown, and you can recall Navier-Stokes equations for fluids, which is also a very complicated set of nonlinear equations, and solution is not unique. However, solutions corresponding to highly symmetric situations can be found by making relevant assumptions about the form of the metric. For example, if the source is spherically symmetric, we can assume that the solution will be spherically symmetric as well. If the source of the left-hand side will be spherically symmetric, such as the distribution of mass m, uniform distribution of mass m, spherically symmetric, we can make an assumption about the line element. We can think that it will be spherically symmetric, and it means that the entries A and B here will depend only on the radial distance from the center, but they will not depend on the angle because there is a spherical symmetry. Okay? This is a plausible assumption. So what we do next, we substitute the solution, this ansatz, into the equations of motion, and solve for A and B with the appropriate boundary conditions, and you discover, so that was Carl Schwarzschild did in 1916, you discover what is known as the Schwarzschild metric, one of the most important solutions of general relativity. So the Schwarzschild metric is given here. It describes the metric of space-time outside of the body of mass m. This outside is extremely important. So if you look at the metric, it's not so different from the Minkowski one, right? Apart from this little element here, 2gm over c squared r, it enters also here. If you put this to 0, for example, this mass is 0, then you're back to Minkowski metric. This element is actually, this piece is actually not very large. So corrections to this 1 is very small for stars and planets. So you can think, I mean, if you think of Earth as a spherically symmetric body, then you can estimate what this correction is, how much the space-time is curved, right here where I'm standing. You can plug in the appropriate distance r, and you calculate this correction to 1. This correction will be of the order of 10 to the minus 9. So it's a rather small distortion of space-time, however, it is still sufficiently large to affect, for example, GPS navigation. So. Note that there is a singularity, so this metric is pathological, it seems, at a certain point, when this whole bracket becomes 0, if it happens at the so-called Schwarzschild radius, and r is equal to 2gm over c squared, then this becomes 0, and this becomes 0 as well, therefore this term blows up. So something happens to the metric, and we need to investigate what exactly. Well, remember that the metric describes the spacetime outside of the body of mass m. So for most objects, this pathology, this singularity, is of no consequence, is no significance. For most objects, the Schwarzschild radius is located deep inside the object itself, and therefore is not relevant for the solution because the solution is on the very outside. For example, for the Earth, the Schwarzschild radius is about 1 centimeter. So this pathology, and the solution is only, so suppose this is This is the Earth, right? The Schwarzschild, this is the Earth. The Schwarzschild radius is somewhere deep inside, and the solution is only very outside. So you don't worry about what happens inside. There is a different solution with the non-zero right inside this distribution of mass. For Sun, the Schwarzschild radius is 3 kilometers, and again, this is a tiny, tiny distance deep inside the Sun. You don't worry about the solution there because the solution is very only outside. However, something happens if some violent forces would squeeze all the matter of a star or a planet inside the Schwarzschild radius. In that case, we will get a black hole. In that case, this pathology is relevant. So if the matter is squeezed inside the Schwarzschild radius, for example, in the process of the gravitational collapse of a star, then we get a black hole, and this is where problems start. So then we have to take this metric and its singularities very seriously. First of all, you have this, what is known as event horizon, at r equal to r Schwarzschild, then this thing becomes 0. And then there is another singularity in the metric. Notice here that if r goes to 0, then this whole term blows up, and the same happens here. So there's another singularity in the metric at r equal to 0. Well, we need to remember that the metric is actually a tensor which looks differently in different coordinate systems. You change from coordinates to coordinates, and you can get rid of some pathological behavior. For example, in 2 dimensions, you have Cartesian coordinates, a line element in flat space is dx squared plus dy squared. You can write the same line element in polar coordinates, and you can say, oh, look, at r equals 0, we have a pathology similar to what happens at Schwarzschild radius, right? This whole term disappears at r equals 0. But we know that we can make a coordinate transformation back to the Cartesian space, and points in r is equal to 0 is no different from any other point in space. So this is a coordinate singularity. This is a singularity that we can get rid of by changing the coordinates. So in a similar way, one can write the Schwarzschild metric in different coordinates, for example, Higgins and Wittgenstein ones, and the metric will be smooth at r equal to rs. No pathology, no blowing up, the metric will occur. However, something will happen as we discuss in this next slide. In general, to check whether we have a true or coordinate singularity, we need to compute something that stays invariant in coordinates are changed, right? Because we need something that does not change when we change the system of coordinates, for example, from Cartesian to polar and vice versa. And such an invariant, one of them is called the Reissner invariant. It is basically a product of 2 Riemann tensors with all indices summed over. For a Schwarzschild metric, this Reissner invariant is proportional to 1 over r to the 6. So this is completely non-singular, then r is equal to r Schwarzschild, but it is singular, it blows up, and r is equal to 0. So out of the 2 singularities, only one is the true one, the non-coordinate singularity at r equal to 0. We don't know. We need to modify physics in order to understand what is happening at r equals 0. But we don't need to modify physics in order to understand what happens at r equal to r Schwarzschild. That's the difference. So what happens at the event horizon? Something interesting happens at the event horizon. We can study the motion of particles in light rays around black holes, just like you study the Keplerian orbits around any star or any other mass source. So let's think about what happens to light. So here is what happens in special relativity. Right, in special relativity, if the observer is located here at the point, let's say P, right somewhere in the center, then there are 2 cones, the past light cone and the future light cone, which means that if the particle, for example, a massive particle, does not propagate, does not move in the reference frame of this observer, just stays there, then it simply propagates along the time axis. Time goes up. If this particle has some velocity, no matter how small, it will not stay at the same space point. It will move in space, and therefore it will move on this graph with some angle, with some slope. Right? The slope will be equal to the speed of the motion of this particle. So the maximal speed we can have in special relativity is the speed of light, and this corresponds to this diagonal motion along the surface of the light cone. So photons, light rays, will move in the future along the surface of this cone, and that's therefore is called the future light cone. So let's see what happens to photons in the vicinity of the black hole, in the vicinity of the horizon. So here are these light cones drawn locally. Light cones outside of the horizon, they look more or less like in the special relativity, but when you come closer to the horizon, you notice that they become a little bit squeezed and a little bit tilted. This is a property of the curvature of space-time, and then, so you can follow these this angle of the light cones, and the light from this point, for example, will only propagate inside the light cone. So the light can only propagate inside this little region here, which emanates from this point. But now, if we come to the event horizon, you can see that the angle with which these light cones are tilted towards the r-axis becomes 45 degrees, and therefore all photons which emanate from the beginning of the light cone here and here, they will only propagate inside this region which is bounded by the event horizon. They will never come outside. They can only come inside the horizon, and eventually they will end up at r equal to 0, where the singularity is, and where we don't know what kind of physics is happening. So this is the property of the event horizon, which is compatible with our understanding of a black hole in sort of the normal terms, right? It's a body whose gravity is so strong that nothing, even light, cannot escape it. So that's a more sort of a function. So let's see what happens in terms of the more advanced physics and the limits of modern physics of black holes. So again, this is the Schwarzschild metric, and you may ask why. So what do we know about the singularity? And the answer is, unfortunately, after 100 years of GR, not so much. We know a great deal about the behavior of particles and fields around the horizon, but we don't really know what is happening inside singularity. One thing to remember is that general relativity is an approximate theory. It's not the last word. It is. So here is an example of Lagrangian of general relativity, where Einstein's equations follow from these two terms in the Lagrangian, but you can easily write down other terms which are invariant, and therefore they can enter the action, and on a quantum level they must enter the action according to the quantum democracy. And if you vary these Lagrangian, you discover that there are corrections to Einstein's equations. We don't know at the moment what kind of coefficients enter these corrections, but generically we can say that corrections to the metric are expected. So the Schwarzschild metric is not the last word. There will be corrections to the metric coming from the so-called high derivative terms, and also coming from quantum loops, quantum fluctuations. Again, we don't know the theory of quantum gravity at the moment. You can think of gravity as an effective theory at large distances in time. Compare this again to fluids, right? We have Navier-Stokes equations which describe the motion of essentially any fluid. But we know that on a very short distance, the fluid is discrete. We have molecules, we have atoms, we have quarks, and so on. So it has a very complicated structure which is not captured by Navier-Stokes equations. In fact, you can generalize Navier-Stokes equations to come closer and closer to this distribution of these molecules and the discreteness of fluid, right? So similarly, gravity, if you want, you can think of gravity as a set of equations, Einstein's equations, as a set of equations which describe this fluid without sort of looking, or fluid of space-time, without looking at the fine details at a very, very short distance. We don't know those details, and this is the front line of the modern theoretical physics. So let's briefly discuss other solutions of Einstein's equations. One of them is Reissner-Nordstrom solution. This is a spherical symmetric distribution of mass m and now charge q. So look at the metric. It is almost Schwarzschild metric with an exception with this additional term here, which depends on the charge. So now this ball is massive, but it also has non-zero charge q. And so we have this term here and this term here. If you put charge to 0, we are back to Schwarzschild metric. If not, then it is a generalization curve. Notice that it has two horizons because we have 1 over r squared, and quadratic equation will give us two horizons. And horizons coincide with solutions of the extremal solution, and they are very important in string theory and other theories. All right, then another solution is even more important. It was found by Kerr in 1963, not so long time ago. It is a solution which describes a rotating axially symmetric uncharged distribution of mass. Its parameters are mass, angular momentum J. So there's a complicated metric also with two horizons and the region called ergosphere in between them. I will not go into detail of the Kerr metric. Just notice that there is another solution, so you can say, why not adding charge to that? And indeed, the solution was found, so you can have a rotating axially symmetric charge distribution of mass, and parameters which completely describe this black hole would be mass, charge, and the angular momentum J. Now, let's come to more advanced topics. the 4 laws of black hole mechanics discovered by Bardeen, Carter, and Hawking in 1973, after studying the metrics, such as the Schwarzschild metric and more generic metrics, they tell us the following. There is a zero law that says that horizon of a stationary black hole has constant surface gravity, k, kappa. You can think of surface gravity as the analog of acceleration of free fall, g, 9.8 meters per second squared, but now not here, but at the horizon of the black hole. That's the parameter which is important for the description of black holes. The first law tells us that in perturbations of stationary black holes, the change of mass is related to the change of charge, angular momentum J, and horizon area by the following quantitative equation. So if you modify the black hole, suppose you take a brick and throw it into the black hole, right, you increase the mass, and other parameters will increase accordingly. The second law tells us that the horizon area A of the black hole is a non-decreasing function of time, only can increase. And the third law, it is impossible to achieve zero surface gravity by a physical process. So what you can do is to compare these 4 laws of black hole mechanics with the laws of thermodynamics. And you find a remarkable coincidence, if you want, or maybe it's not a coincidence, right? So the zeroth law of thermodynamics tells us that the system in thermal equilibrium has a constant temperature T, right? It's very similar to the zeroth law of black hole mechanics. The first law of thermodynamics is the law of conservation of energy. It tells us that if you change the energy of a black hole, then the entropy of the system changes, and there are some work terms around. The second law, which is even more important, tells us that the entropy of a thermodynamic system is non-decreasing function of time. And the third law says that it's impossible to achieve zero temperature by a physical process. Is it a coincidence, or perhaps there is a deeper connection between the laws of black hole mechanics and the laws of thermodynamics? You are tempted, perhaps, to identify kappa with some coefficient with temperature and area with the entropy of some system, but it's not clear how. In 1972, Jacob Bekenstein suggested that the black hole should have a well-defined entropy proportional to the horizon area, as in the previous slide. And he was actually laughed at by many researchers because black holes are black. They do not radiate, do not emit any radiation, and therefore cannot have a temperature associated with them. So what it is about. However, in 1974, Hawking demonstrated that black holes actually do emit radiation at a quantum level. And so one can, in fact, associate a temperature with them. So that was a rather dramatic advance. So here are some formulas. So Hawking showed basically that black holes emit radiation with a black body spectrum at a temperature given by this expression. Notice the presence of the h bar. So it is a process which happens at the quantum level. And you can see from this formula that the Hawking temperature is inversely proportional to the mass of a black hole. So if you have a supermassive black hole, its temperature, the Hawking temperature will be very small. You can look at these numbers and calculate this out. However, if the black holes are extremely small, for example, primordial black holes or Big Bang, then the temperature will be sufficiently large. So, for example, black hole of 1 solar mass has a Hawking temperature of about 50 nanokelvin. So this fixes the coefficient of proportionality in Bekenstein's conjecture, and the Bekenstein-Hawking entropy is indeed proportional to the horizon area, given horizon area, and again, notice the presence of h bar downstairs. So there are some immediate consequences and immediate problems which are related to this identification. First of all, black holes evaporate with time. You see, from this expression, it's almost obvious that they have negative specific heat, right? So what happens if there is a temperature of a black hole, suppose it radiates some of its mass, so the mass decreases, mass decreases, this n becomes smaller, then therefore temperature becomes larger, right? And eventually, this black hole will evaporate. The question is what happens after it evaporates. It emits a black body spectrum. It's completely featureless. There are no imprints of any information which was ever thrown into a black hole. So you can throw in a black hole any sort of complicated systems, which books, not books, but so some complicated systems, right, which contain some non-zero information, and in the end, when black holes evaporate, only radiation, featureless radiation remains. It seems. Maybe we don't understand something in the very end of this process, but it seems this way. This is known as the information loss paradox, which has not been resolved until now. In fact, it's not completely clear even now what is happening with it, but there are some advances which I may talk about later on. The most important question, however, is the following. What are the microscopic degrees of freedom underlying the black hole thermodynamics? Remember that thermodynamics is also an effective theory, like in the usual systems. We have normally, microscopic level, we have a statistical mechanics with the notion of temperature, entropy, and so on, emerging from the dynamics of the microscopic quantum systems. So the example of this, the simple example of this, is the system of particles with a spin, right? So suppose we have one particle with spin. It has two microstates. The spin can be up or down. If we have two particles, a system of two particles, then there are more options. Both can have spin down or spin up, or in the opposite directions, right? So there are altogether in one particle we have two microstates. For two particles we have four microstates. Generically, if you have n particles with spin, the number of microstates is equal to 2 to the power n. And Boltzmann told us that the entropy, the usual thermodynamic entropy, on this microscopic level can be calculated as a logarithm of the number of microstates. And in this case, the entropy, you can easily calculate, is proportional to the number of degrees of freedom of this quantum system. What happens with black hole? We know that black holes have entropy. Bekenstein-Hawking calculated this entropy. But this entropy, what are the microstates which we want to count in the similar fashion like here to get this entropy in a microscopic system? Can we count the microstates of the black hole and recover the Bekenstein-Hawking result? What are the microstates of the black hole? This is a fundamental question, and people attempt to, for many years, they attempt to solve this problem, and there is a partial progress in this direction. In particular, the strongest one probably is by Strominger and Waffer in 1996. We were able to count the microstates of a very special supersymmetric black hole in 5 dimensions. Yeah, it's a far cry from a Schwarzschild black hole, which sits in the middle of our galaxy and so on, but nonetheless, it is a model which achieves this success, that the result coincides exactly with the Bekenstein-Hawking thermodynamic entropy. The reason why they had to resort to this special black hole, supersymmetric black hole, is the following. What they do basically is, there is a construction of strings and topological objects in string theory known as branes. You can count at weak coupling, you can count microscopic states of the system, just like you do in statistical mechanics, a system of spin. Then you squeeze this whole thing beyond the Schwarzschild radius, it becomes a black hole, and you can compute the Bekenstein-Hawking entropy as you usually do. And then you compare these two results. But you must be sure that in the process of squeezing in, you don't lose any states. So this is protected by supersymmetry and these other special properties. Without these special properties, you cannot be sure. You hope it is not the case, but there are no theorems that guarantee that. This is a major difficulty here. So Strominger and Waffer result has been generalized in many ways since 1996. However, we still do not know how to count the microstates of the normal black hole, for example, the simple Schwarzschild black hole in 4 dimensions. Nonetheless, it has profound consequences, these calculations. Well, let's talk about the holographic principle. So in thermodynamic systems without gravity, the entropy is extensive, proportional to volume. You think of a gas or some fluid, and the entropy of the system will be proportional to the volume this gas occupies. But notice that the Bekenstein-Hawking entropy, which we just discussed, is proportional to the area, the horizon area of the black hole, not the volume which occupies that the black hole occupies. It is proportional to the area. And it seems that the gravitational degrees of freedom in d dimensions, generically, are effectively described by some theory in d-1 dimensions. This is known as the holographic principle, which was first discussed by Rudolf and Susskind in 1992. So again, gravity, the system with gravity occupying some volume, the effective degrees of freedom seems to live on the boundary of this region and in lower dimension. So this development resulted in what is known as the gauge stream duality, sometimes also is known as ADS-CFT correspondence, and it's basically the same statement, and it grew up. It's important to understand that ADS-CFT correspondence grew up out of attempt to understand black hole entropy. So in the open string picture, you have dynamics of strings and branes at low energy, and this dynamics is described by quantum field theory without gravity, some gauge theory or some quantum field theory. You squeeze this whole thing beyond the horizon radius, and now you have a closed string picture. Dynamics of strings and branes at low energy is described by gravity and other fields in higher dimensions. And you conjecture the ADS-CFT correspondence is a conjecture, despite the fact that It survived many tests, but it is a conjecture, not proven. The conjecture is that this side is exactly equivalent to this side. It's exactly equivalent, so it should be forwarded by Moldasen and then developed by Gupta, Ivanov, and Witten in 1997, 1998. So that's all good. So we know that, all right, so there is some microscopic system that describes our black holes. It describes them in thermal equilibrium, as we saw. The laws of black hole thermodynamics, the laws of black hole mechanics are identified with Bekenstein-Hawking entropy and Hawking temperature. But what about black holes beyond equilibrium? So undisturbed black holes are characterized completely by global charges such as mass, total electric charge, and total angular momentum. And thermodynamic system in equilibrium is also characterized by conserving charges. Total energy, total electric charge, total angular momentum. So this is not very surprising. Now what happens if one perturbs a non-gravitational system, for example, a spring pendulum like this one, it will oscillate with eigenfrequencies, known as normal modes, right, the usual pendulum, right? So, and these eigenfrequencies, they depend on the system itself. So for example, for this object here, the eigenfrequency will be simply square root of the spring constant divided by mass. And of course, in more complicated situations, it will be not just one frequency, it will be the full spectrum of these frequencies, but it can be found. And what is crucial, it depends on the system itself. It does not depend on the force that perturbs the system. It is a characteristic of the system itself. So what happens to black holes? Suppose I want to do the same with black holes. I want to perturb my black hole, right? I want to throw some stuff in it and make it oscillate. Can I find the spectrum? What happens if one perturbs it? Can I find the spectrum which characterizes these black holes and how the spectrum is encoded into this microscopic degree of freedom that I was talking about? So ATS-CT correspondence of H-string duality gives a quantitative way of comparing and studying the spectrum and identifying the ingredients of this spectrum. So look at the left side of this slide. So you have some black hole or black brane characterized by these conserved charges, and it has Hawking temperature and Bekenstein-Hawking entropy. Now suppose you perturb the black hole. The original metric is perturbed by this little h mu, and using Einstein's equations, you can write down precise equations which describe these fluctuations h mu together with the appropriate boundary conditions. The important difference between the normal modes, like a pendulum and so on, and the black hole oscillations is the presence of the horizon. Classically, if we don't think about quantum effect like Hawking radiation, classically, any stuff which goes inside the horizon disappears there forever. And therefore, our system is not a normal mode system anymore, because information, part of the information in the system is lost once it crosses the horizon. You can think of some quantum well, for example, right, an infinite well with semi-transparent walls. So part of information is leaking out. So suppose this is the horizon and part of information is leaking out. So the spectrum will not be real in this case. It will reflect the fact that the boundary value problem is not Hermitian. It is known as a quasi-normal spectrum. It will acquire some non-zero imaginary part. This is exactly the same. What happens is qualitatively, this is the same as happens if we take a usual non-gravitational system and deviate it from equilibrium. What will happen? Deviate from equilibrium, the system goes back to equilibrium, right? There will be some diffusion, or there will be a sound wave, for example, right? If I perturb the air in this room, well, there's some more important law. There will be a sound wave. The sound wave will not propagate forever. It will attenuate, it will die eventually. It will die because the dispersion relation for the sound wave has a non-zero imaginary part proportional to viscosity. See, there is a friction in the air, and here is the dispersion relation for the sound. You can see the part which describes the propagation of sound, and then there is the attenuation part, which is proportional to the viscosity entropy ratio. So from this previous slide, it is clear that if we identify the microscopic system which describes our black hole, we must find the quantitative identification between quasi-normal spectrum of black holes and the spectrum of microscopic system, and that has been done. So one simple example is the following. This is the spectrum of a black hole. The honest calculation from gravitational side, and this is the dispersion relation which is expected from the point of view of a field theory of microscopic degrees of freedom. By comparing the two, you can see that the speed of sound is speed of light divided by the square root of 3, and you can compare these two terms and read off the ratio, viscosity entropy ratio, and other quantities of the microscopic system. Moreover, one can go on and relate Navier-Stokes equations of this fluid of these microscopic degrees of freedom and Einstein's equations quantitatively. This has been done around 2007, 2008. So this is a very recent stuff. All right, coming to the end. So we have some conclusions. Black holes, I hope you also believe fascinating objects from the theoretical point of view at least. They test a little bit of our knowledge. Any distant candidate for a theory of quantum gravity must be able to explain their properties. And this is a must. Black holes have entropy and temperature and behave like thermodynamic objects. We think we know why, because of the holographic principle. We know that in some models, in some cases, we are able to identify the precise degrees of freedom that govern the behavior of black holes. Black hole spectra of excitations encode non-equilibrium properties of this dual microsystem, such as viscosity on the previous slide, and many other properties. We do not know how to resolve the black hole singularity. This is a puzzle that's been with us for many, many, many years. That requires quantum gravity. Einstein's gravity is an approximation. It is an effective theory. Remember this analogy between gas Stokes equations and fluids. We do not know the full theory at the quantum level. This is both frustrating and also interesting. And we should also not forget about the practical application, because all this talk was about the theoretical concept of black hole, how black holes are derived, what their properties are from a theoretical point of view. But we should not forget about practical applications and real black holes. For example, real black holes in our very own universe. And talks by John Magaran and James Binney next will introduce precisely these real black holes.